Hello, good evening to all. So in previous lecture we discussed about the electric lines of force, and in this class we discuss about electric flux, Gauss law and its various applications. Okay. So when we take discussion about the electric flux, then what we find, electric flux is a measure of number of electric lines of force associated with a particular area. Okay. Electric flux generally represented as a symbol of phi. Okay. And electric flux is always a scalar quantity. Okay. So generally the electric flux measures the number of lines of force associated with a certain area. Okay. And from that lines of force we can measure the electric flux, or what is the magnitude of the electric field associated with that surface. Okay. Suppose I consider here a surface area S, and within that surface I consider a small region. Okay. And from that small region there will be the passage of the electric lines. Passage of the electric lines, and these electric lines has a definite electric field vector, suppose E. Okay. And if I consider a small surface here, suppose that surface is ds. Okay. And this one is the surface vector n cap, or simply ds vector. Okay. And if the electric field measures makes an angle of theta in between E vector and the ds vector, in such case we can also give a mathematical form to calculate the electric flux. Okay. So simply we can say the electric flux is a measure of calculation of number of electric lines of forces associated with a certain area. Okay. Or mathematically we can say electric flux is a dot product of electric field intensity with the area of the surface vector. Okay. So that's why we can say electric flux phi equals to a dot product of electric field intensity with the surface vector. Okay. So phi equal to E dot S. E is the electric field intensity, S is the area of that surface. Okay. So phi equals to, that is the mathematical form to calculate the electric field and calculate the electric flux. Okay. So phi equal to E dot S, dot product of, or the scalar product between electric field intensity with the area of the surface vector. Okay. So that is why we can say phi equal to, so there is a dot product, means there is a cosine of angle between electric field and the surface vector. So that is Es cos theta. Okay. So Es cos theta. Okay. So that is the mathematical form to evaluate the electric flux. Okay. But the electric flux is maximum. Okay. Phi is maximum when we take theta as 0 degree. Okay. Phi is maximum because when we consider theta as 0, then cos theta, that will be 1, and in such case Es we obtain, that is phi equal to Es. Okay. So maximum flux we will obtain if surface vector and electric field lines always parallel to each other. Okay. So when electric field and the surface vector are parallel to each other, in such case we measure a maximum flux. Okay. And phi is 0, phi is 0 when theta equals to 90 degree. Okay. So if theta equals to 90, then cos 90 equals to 0, and in such case phi is also 0. So if electric field intensity and the surface vector lies perpendicular to each other, in such case we measure a 0 electrical flux. Okay. So electric flux is the dot product of electric field intensity with the area of the surface vector, okay, or it is a measure of number of electric lines of forces associated with a certain area, okay. So, what is the unit of electric flux and what is the dimension of electric flux? Unit of phi, okay. So, as we say phi equal to E dot S. So, simply we can say unit of electric field, that is Newton Coulomb inverse, okay, and S is area. So, that is why meter square. So, Newton meter square divided by Coulomb. CGS unit, that means we can say Dine centimeter square divided by Coulomb. So, that is the CGS unit to measure the electric flux, okay. So, what is the dimension? Dimension of phi, okay. So, phi equal to E dot S, okay. Simply we can convert E equals to F by Q dot S, okay. And if we take the dimensional analysis, F, that is M1 L1 T minus 2 with S as L2 area vector. So, charge, that is A1 T1. So, that is M1 L3 T minus 3 A minus 1. So, that is the dimension of electric flux, okay. Then comes to an interesting thing, that is Gauss law, okay. Important thing, Gauss law, okay. So, what is Gauss law and what is its uses, okay. Gauss law generally measures the number of or the electric flux associated with certain surface, okay. And by using this concept, we can evaluate the electric field intensity for any type of surface, okay. So, what Gauss law says, okay. Gauss law gives a measurement of electric flux through any charged surface, okay. That means we can say the statement of the Gauss law, okay, it states that, okay, it states that the net outward electric flux, through any closed surface, okay, the net outward electric flux through any closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface, okay. The net outward electric flux through any surface is equal to 1 by epsilon naught times the net charge enclosed by the surface. So, let us write, that will be easy to understand you. So, it states that the net outward electric flux, through any closed surface, is equal to 1 by epsilon naught times the net charge enclosed by the surface. Okay. So, the net outward electric flux through any closed surface is equals to 1 by epsilon naught times the net charge enclosed by the surface. So, mathematical form, So mathematically we can represent phi equal to close integration s E dot ds, okay, is equal to q by epsilon naught. Okay, so that is the mathematical form of Gauss law in electrostatics. Okay, phi, that is closed integration s, as we are considering the surface must be a closed surface. Okay, closed integration s E dot ds equal to q by epsilon naught. That means the net flux through any closed surface depends upon the net charge enclosed by the surface. Okay, it does not depends upon its radius, it does not depend upon its size. Always the flux enclosed through any surface always depends upon the net charge lies within the surface. Okay, so the total flux depends upon the total charge on a surface. Okay, so let us prove the Gauss law. Okay, so make a simple proof. Suppose I consider here any surface, okay, of surface area S, okay, any closed surface of area S, and within that surface there is a point charge q lies at O. Okay, within the surface I consider there is a point charge. Okay, so total charge on the surface is q. Okay, and I take here a observation point, that is P. Okay, I take here there is a point of observation on the surface of that surface. Okay, on the surface of that region. Okay, and the point of observation is at a distance of r. Okay, from that point charge. Okay, I mark here there is a small region, there is a small surface. On that big surface I mark a small surface. For example, if this one is a big surface and I take here a small surface region, okay, a small surface region on that big surface. Within the surface I consider here a small surface, and that small surface I consider at the point of observation. Okay, suppose the surface area of that small surface is ds. Surface area of that small surface is ds, as I consider the point charge is positive. Okay, for the positive point charge the electric lines of force are away from the point charge, plus positive charge the electric lines of force are always away from that positive charge. Okay, so that's why when I consider here there is a positive point charge, means there is also the electric lines of force away from that positive charge. Okay, suppose this is the direction of the electric field intensity. Okay, these are the direction of electric lines, means these are the direction of electric field intensity. Okay, and this one is a small surface. Suppose this one is the surface vector. Okay, ds vector, and angle between electric field and ds vector is theta. Okay, and suppose we join that small surface towards the point O. Okay, suppose we join that small surface. Okay, so here as the point charge P at a distance of r from the point of observation, means we can say at the point of observation we can measure the electric field intensity. Okay, so electric field intensity at P, electric field intensity at point P is E equals to 1 by 4 pi epsilon naught q divided by r square r cap. So that is the electric field intensity at point P due to the point charge q. Okay, and if I consider the electric lines of force passes through that small surface ds. Okay, suppose this amount of electric lines of force passes through the small surface ds. okay, then we can measure the flux associated with that small region, because flux is the dot product of electric field intensity with the area of the surface vector. Okay. So, that is why the electric field intensity passes through the small area ds is E. Okay. So, the electric field intensity, the flux associated with area ds vector, area ds is d phi equal to E vector dot ds vector. Okay. The small flux associated with the small area, that is E vector dot ds vector. So, what is the net flux? What is the net flux? If I consider the small surface ds here, like this, and large number of small surfaces, then in total calculation we can add all the surfaces or all the electric fluxes, or simply we can integrate. Okay. So, the net flux associated with the total area S is phi equal to integration d phi. Okay. Phi equal to integration d phi. Okay. And as the surface is a closed surface, so that is why we can use this as closed integration S E vector dot ds vector. Okay. E vector dot ds vector. So, that implies to phi equal to closed integration S, substitute the value of E, that is 1 by 4 pi epsilon 0 q divided by r square into r cap dot ds vector. Okay. So, this one is r, that means we can say this is also direction of r cap. Okay. Radial vector. Okay. So, that is why take common outside, q by 4 pi epsilon 0 close integration S, okay, r cap dot ds vector divided by r square. Okay. R cap is a unit vector and ds vector. This one is unit vector, this one is ds vector, angle between them is theta, and there is a dot product, means there must be a cosine angle. Okay. So, that is q by 4 pi epsilon 0 close integration S ds cos theta divided by r square, ds cos theta divided by r square. So, ds cos theta divided by r square is known as solid angle. Okay. ds cos theta divided by r square is known as solid angle. So, that is q by 4 pi epsilon 0 close integration S, that is represented as d omega. Okay. So, that is d omega equal to ds cos theta divided by r square, that is called solid angle. Okay. So, q divided by 4 pi epsilon 0 into the total solid angle, if I consider the total solid angle, closed integration S d omega, the total solid angle is 4 pi. For any surface, the total solid angle is 4 pi. So, that is why if we cancel, then what we find, phi equal to q divided by epsilon 0. Okay. Q divided by epsilon 0, and we start from E dot ds. So, as a whole we can write phi equal to close integration S E dot ds equal to q by epsilon naught. So, that is called Gauss law in electrostatics. Okay. Gauss law in electrostatics, that is phi equal to closed integration S E dot ds equal to q by epsilon 0. Okay. So now we can take two different special cases in order to measure the electric flux. Suppose the first special case, suppose I consider that surface, instead of containing a single charge, it contains large number of charges. Instead of containing a single charge, there is a large number of charges Q2, Q3, Q4, Q5 like this up to Qn. Okay. As we say, the total electric flux depends upon the total charge enclosed by the surface. Okay. So this surface contains Q1, Q2, Q3 like Qn number of charges. So if a surface contains large number of charges, then in such case the total electric flux phi equal to closed integration S E dot ds equal to summation over q divided by summation over I equal to 1 to n qi divided by epsilon 0, or summation q1 plus q2, that means the net charge enclosed by the surface. Okay. The second case we can say, if the charge lies outside the surface, okay, if the charge lies outside the surface, then flux must be 0. Then flux must be 0. Okay. When the charge lies outside the surface, that means within the surface there will be no charge, and when there is no charge means there is no flux associated with the surface. So in such case phi equals to 0 as q equals to 0. Okay. Charge associated with the surface is 0, that is why flux linked with the surface must be 0. And the important thing that you have to remember, that the flux does not depend upon the shape of the surface. That means if we increase the radius of the surface to twice, if we increase the volume of the surface, then flux remains unchanged. When we change the charge, there must be change of flux. Okay. A question arises like, if we double the radius of a sphere, okay, if we double the radius of a sphere, how the flux changes? Okay. The electric flux remains same. Okay, as electric flux does not depend upon the shape of the surface, it only depends upon the net charge enclosed by the surface. Okay, understand? Now let us take one application of Gauss law. Application of Gauss law. Okay, that is derivation of Coulomb's law. Derivation of Coulomb's law from Gauss law. Okay, derivation of Coulomb's law from Gauss law. Okay, as we know, Coulomb's law is valid only for a point charge. Okay, and we can use the application of Gauss law by taking a suitable Gaussian surface. Okay, so what is a Gaussian surface? A Gaussian surface is a imaginary surface that enclose all the electric lines of forces associated with a charge region. Okay, associated with a charge region. Okay, that is a imaginary surface that enclose all the electric lines of forces. So in order to evaluate the Coulomb's law, suppose I consider here there is a point charge q. Okay, and a point of observation, suppose P, and the point P is at a distance of r. Okay, so in order to measure the Coulomb's law by using the Gauss law, we can draw a imaginary surface, okay, that enclose all the lines of forces associated by a point charge. Okay, so the Gaussian surface that for a point charge must be spherical, because we say for a point charge the electric lines of force are in all direction and this ends at the infinity. Okay, so that's why for a point charge the electric lines of force is spherical. Sorry, for a point charge the Gaussian surface must be a spherical surface. For line charge the Gaussian surface is cylindrical. Okay, so let us imagine a Gaussian surface of radius r, okay, that encloses the charge q. Okay, so this is a imaginary Gaussian surface that is drawn by taking a radius r, and that imaginary Gaussian surface passes through the point of observation P. Okay, so as P is a point charge, means electric lines of force are outward direction. So in such case, in order to measure or in order to use the Gauss law, we can take here a small surface of surface area ds, and as it is a positive charge, so electric lines of force is in this direction. Okay, and the surface vector is also lies in the same direction. Okay, the surface vector and electric field are in the same direction, so that's why here theta equals to 0 degree. Okay, so we can use the Gauss law like, and the surface is a spherical surface. Must remember, for a point charge the imaginary Gaussian surface must be spherical. Okay, so according to Gauss law, close integration s or phi equal to close integration s E dot ds equal to q by epsilon 0, because when you use the Gauss law for this spherical surface, okay, the net charge enclosed by the surface is q. Okay, so as for the Gauss law definition, so close integration s E dot ds equals to q by epsilon 0. So that implies to close integration s. So what is the aim of Gauss law? Aim of the Gauss law, we can say, always Gauss law is used to measure the electric field intensity associated with the surface. Okay, so electric field and the surface vector are along the same direction, so theta equals to 0. So that's why E ds cos 0 equal to q by epsilon 0. Cos 0 equals to 1. So close integration s E ds equal to q by epsilon 0. So if you take, that is integration over a surface, so take outside the electric field, so close integration s ds, that is q by epsilon 0. Okay, ds is the surface area. Okay, and a sphere has a surface area of 4 pi r square. If the radius is r, what is the surface area of the sphere? The surface area for the sphere is 4 pi r square. So that's why, so here we can substitute value, that is E, not in vector form, E into 4 pi r square equal to q by epsilon 0. Okay, so that implies to E equal to 1 by 4 pi epsilon 0 q by r square. So that is the electric field intensity for a point charge. That is the calculation of electric field intensity for a point charge. Okay, now if I take, okay, if I take a test charge at point P, okay, also we say electric field has a property that it measures the amount of electric force acting on a charge particle. Suppose we place, if we place a test charge at, if we place a test charge q0 at point P, then the electric field at point P measures the amount of force acting on the point charge. Okay, then force on that charge, is F equal to Q naught E. Okay, so F equal to Q naught E. So that implies to F equal to, substitute the value of E, so that is 1 by 4 pi epsilon 0 q naught divided by r square. Okay, and this is called Coulomb's law. Okay, this is called Coulomb's law in electrostatic. Okay, so that's why we derive Coulomb's law by using the Gauss law. Okay, so if there is a question arises, calculate the expression for electric field intensity for a point charge by using Gauss law. That means you have to solve up to this limit. Okay, up to this. Okay, you can solve. Okay, that is the electric field intensity for a point charge. Okay, understand? Thank you.